All right, here we go. This is problem number 47 from chapter, what are we in, 6 here of Halliday and Resnick. All right, so it says Roy, who has a mass of 80 kilograms, is on a Ferris wheel. It's going around in a vertical circle with a radius of 10 meters, and he's traveling at a constant speed, so we should automatically be thinking uniform circular motion, right? Because his speed isn't changing. So that's the deal. He's going around in a circle like this. A says to find the period of motion, so hopefully that wasn't too bad. We know that velocity is 2 pi r, the circumference, divided by t, the period, the time to travel that circumference. So algebraify this equation, and you get v equals 2 pi r over v. Plug in your numbers, and you get like 10.3 seconds, which, after sig digs, is 10 seconds. Okay, so that's part A. There wasn't a whole lot to that. So, all right, now part B. So to find the magnitude of the seat's normal force on Roy when he's at the highest point of the circular path. All right, so because we're talking about forces and we're talking about uniform circular motion, it definitely probably makes sense to take a second and think about centripetal force. Well, here we know our mass, our radius, and our velocity. So we can calculate our centripetal force just by doing mv squared over r, right? And so our centripetal force, if you figure it out, turns out to be 297.68. We'll hang on to those extra digits until the end. So now remember, because this is uniform circular motion, that centripetal force is not going to change. The entire time he's going around the circle, that's the centripetal force. Now, what provides that centripetal force is what changes, right? So let's take a look at part B. So part B says to find the magnitude of the normal force when he's at the highest point of the circular path. So here's the circular path, right? So he's right here. Okay, and so the idea is gravity is going to be pulling him downwards, and we got to find our normal force. So let's take a second to do this. So here's Roy. Gravity is pulling him down with a force of 80 times 9.8, which is negative 784 newtons. Okay, and then the C is holding him up. All right, but so remember, when you're talking about circular motion, because we're talking about uniform circular motion, the speed is constant. The only thing that's changing is the direction. So all of the acceleration is centripetal acceleration. So remember, the whole idea here is Newton's second law tells us that net force is mass times acceleration, right? But this acceleration, when we're talking about uniform circular motion, is all centripetal acceleration. And as a result, our net force is simply just going to be our centripetal force. Okay? So over here, here's what we've got. We've got that our net force is our centripetal force, and that, for us, is equal to the force of gravity plus the normal force. So for us, our centripetal force is 297.68. That's got to equal our gravity, negative 784, plus our normal force. Now, before we go any further, we need to stop and address our signs. Remember, when you use the centripetal force equation, it's just giving you the magnitude of the centripetal force. It's telling you how big it is, but it doesn't tell us the direction. So when we're doing part B, remember, your centripetal force is always directed towards the center of the circle. So for part B, the centripetal force is going to be negative 294. Right? Because in order to keep him going in a circle, we need a downward net force. Okay? And so what this is telling me is that my normal force is basically 297 less than my force of gravity. But anyway, do the algebra, add 784, and you figure out that your normal force is pretty close to 490 newtons. Okay? So notice the normal force there at the top of the right is less than the force of gravity. That's because we're sort of allowing Roy to fall a little bit, right? We want gravity to win because we want to provide that downward acceleration to change his direction there at the top of the path, okay? So that's the deal for part B. Now, man, the smartboard is not cooperating with me today. Okay, so now when we do part C, let's see, we can do this one in red. How about, so when we do part C, now we're down here, so here's our circle. Gravity's pulling down, but our net force, our centripetal force, has to be upward, right? Because, you know, your oops, sorry, this is supposed to be force of gravity down here. Our centripetal force has to be upward to stop the downward motion and begin the upward motion, okay? So it's the exact same calculation. Once again, our net force is going to be our force of gravity plus our normal force, right? So here's Roy. Gravity's pulling down with a force of negative 784 newtons. And so the question is, what does this normal force need to be to give us the right centripetal force? But the difference is this time our centripetal force is, instead of being negative like it was in part B, our centripetal force is now positive. So now my net force is positive 297.68. That's going to equal my force of gravity, negative 784, plus my normal force. Okay, and so solve it. Add your 784, and your normal force here turns out to be right around 1100 newtons. Okay, and so the idea is now my normal force is much bigger than gravity, because the normal force is not only preventing him from falling, but also stopping downward motion, beginning upward motion. It's like stopping your downward motion in an elevator. Okay, so there we go.